No packets out, open to where we left off before. And we're going to fill in for today. And then we're going to bounce over to where we need to go. All right. So, today is 9/16. Oh, wait, we didn't do it the other day. What day was this? 9/14? 9/16, we took our quiz already. We're going to do some notes on continuity. And your homework is going to be the evens from this worksheet and limits worksheet B, which is due next class that you got a while ago. Now, let's bounce over, please, to you're going to hand your homework for the first 30 and at the end of the period. There is this, we proceed out. Here. All right, as we proceed out, we're going to talk about continuity. Does anybody, I don't know if Weiss or I think Jockman did it as well, but did anybody that I have remember the holy trinity of continuity, or the three things that you need to show in order to show continuity? We got two people, and it should by now make sense. You're trying to show that a graph is continuous, meaning there's no interruptions to it. What? Hang on, let me see. I think I typed it out. What he said was correct. The left-hand limit is equal to the right-hand limit. Okay. So what we're going to show is the limit as we approach C from the positive side is equal to the limit of our function. By the way, let's not be lazy Larrys with our notation. Is equal to the limit as we approach this. The limit as we approach from the left is equal to the limit as we approach from the right, which is going to be equal to the function value at some C. Let's make this a different color. Let's do red. Color of passion, which is what we should be about our calculus. Somewhere at the top of your paper, order, bring to front, you're going to want to get this down nice and big. That, little loves, is the definition of continuity. The limit from the positive side as we approach any number is equal to the limit from the left. So they're converging on the same values everywhere. The left and right hand sides are always going to meet, and at that value, the function value equals what those limit values are. Make sure that that's down. If you want to go, I think White Tiger in the Village is having a special until the end of the day. You can get it tattooed on yourself for $25. Okay? Now, functions that are continuous are smooth and have no gaps to them. The sine wave is one of them. A line is one of them. There are no gaps or holes or jumps. A function is continuous if, well, we talked about it before, the limit from the left is equal to the limit from the right, which is equal to the function value. So, actually, let's do this. Can anybody sketch for me a function that meets these two requirements and will not be continuous? Hands up, please, if you can tell me. Give me a picture of something that meets these requirements and is not going to be continuous. We'll have you come on up and sketch them out. You want to give it a try? I mean, stand up and do it. Think about, because a lot of times we're going to talk about these and you need to be able to give an example and or a counterexample. Does this work for every value? Yes or no? we're going to say, all right, I'm going to sketch out now something that doesn't meet the trinity. It meets the definition from the left and the right. There you go. Is the limit from the left equal to the limit from the right? Yes or no? Is it continuous? No. So a function is continuous if the function value is defined at that specific value, the limit exists, and the limit is equal to the function. That's the lesson. Some people go through and use that as the definition. I hate it. It's too much. These three types, when they say the trinity of continuity, they go through, this is the textbook definition. The AP takes the definition that we did before. Does the left-hand limit equal the right-hand limit, which equals the function value? If all of those stars line up everywhere along the graph, it's going to be continuous. And we're only going to be looking on the vast majority of them at the problem areas. There's different types of discontinuity. The first type is removable, and a removable one is if there is a hole in the graph, which we can plug in and close off. Now, to go back, this was Thomas's example here, right? Now, let's say this is what he gave us. This has point discontinuity because it's not continuous at a point. Can we fill this in? Sure. And make it continuous? We could say, all right, it's undefined everywhere, but let's say -4. Now I'm going to make it a piecewise function. It's undefined everywhere but -4, but I'm going to define it at -4, and that way we can move on. Next type is if there's a jump discontinuity, which is when the one-sided limits have different values. There's not going to be much we can do to fix that. Infinite discontinuity. That happens when we have a vertical or horizontal asymptote, and the one-sided limits are going to go to positive infinity or negative infinity. Because if there is an asymptote, you just say, all right, well, let's plug that asymptote in. And then the last thing is there oscillating discontinuity, which is something like this. We talk about oscillating functions back and forth. There's no limit available because it's going to be bouncing around like crazy. There's nothing you can do to hold it down in a specific spot. Questions on those? Bounce over, please, to the next page. Now, and I think this was my fault too. My pages are going to be different than yours for the rest of the packet because of the spacing in Microsoft Word. See how that one page? What is it? Page? Which one is it? 15. What a joke. What a dummy I am. See how it snaked over that graph was given to you. Now, hands up please, you tell me what 1 over x squared is going to look like. Okay, what's 1 over x squared that was on the functions, the parent functions that we gave you before? Think about an x comma y or an input-output table. What is that graph going to look like? Lucky for you all, let the fun begin. Oh. You're going to ruin someone's day. If it's not you, I will make it you that I call on. Okay, pick someone.
I'm trying.
Okay. Kanji. Think about what the graph, do you know what the graph that's going to look like? Where is there any problem areas without going to the calculator that you can see? Zero. Zero is a problem area. So let's think about it. What happens is I start plugging in, think about it as an x comma y, right? is I plug in huge negative values. What is the function value going to? Like I plug in negative a trillion. No. It would be positive because you take a negative and square. So what's 1 over a trillion squared going to give you? A really small number. It's getting essentially close to 0. So we know our horizontal asymptote. We know our horizontal asymptote is going to be at x equals 0. We have a vertical asymptote as well at y equals 0. The same thing's going to happen as we go to positive infinity. What does that mean we're going to get? Something that looks like that. So now you're going to sketch, I know. Now you're going to sketch that out. You don't need to include the third and fourth quad if you don't want to, because nothing's going to get graphed there. What type of discontinuity do we have? Taking a look at that graph, what type of discontinuity? Mike, what are we going to have? Perfect. So we've graphed it. Now we're going to identify this as having an infinite discontinuity. And the directions to say, determine points of discontinuity, identify the type. So where is this discontinuous? At what? 0. Is it continuous everywhere else? Yeah. If it's removable, then redefine the function as a piecewise function that is continuous. Where is this function discontinuous at again? So we're going to give this out, and I love this. We're going to say f of x is equal to, give a nice, very classy bracket, and this is going to be 1 over x squared for every x that isn't equal to 0. So everywhere that x isn't 0, we're fabulous. Where's our problem at? I'm going to make this continuous by plugging something in for 0. Give me a number you want the function to have when it's 0. 5? All right. Now, so I did this. I plugged this in, right? And I go, is x is equal to 1, 2, 3, 4, 5. All right. Did I just make a continuous function? Oh, I love it. No. The left and right limit values are equal. What is the left-hand limit and the right-hand limit going to? Those one-sided limits, what are they going to? Positive infinity. What's the function value at 0? We define, according to our new function, we made it be 5. Even when we fill it in, is it continuous now? Why not? No? The full limit would go, what's the problem? Why wouldn't this be continuous? The left...
Because the limits still don't go, they don't converge on
the left-hand limit and the right-hand limit equal each other, but they don't equal the function value. Now, does the limit itself even exist? No. You're right, but you didn't reference the fact that the left and right limits, that the limit doesn't equal the function value. That's the bigger piece. So is this going to be a function? Or continuous, excuse me. No. Is it a function? Absolutely. And by the way, is there any way that we can go through and make this be something that is continuous? No. You're stuck. You are stuck. Now, the problem that we're going to have is this. Think about graphing out 2. Is that continuous everywhere? Hands up, please, when you can give an articulate answer. Is that continuous everywhere? Molly? Where's the problem area? Now, not only do we need to indicate that it's not continuous at 2, but let's be on the lookout for the type of discontinuity that we're going to have. Why do you know it's, well, I'm going to say this. Before you jump to it being a hole in the graph, which is secondary, I'm going to plug in my problem area, which you said, Molly, was what? 2. So when I plug a 2 in, I get a 0 in the denominator. What do I get when I plug a 2 into the numerator? What's that called? Indeterminate form. Hands up, please, if you can tell me what indeterminate form indicates that we should be on the lookout for. Kevin? Let's factor this down. Hands up, please, when you can tell me what this function, this f of x, this numerator, is going to factor down to. Hands up, please, when you can tell me what that would factor down to. 2 people. Hang on, I'm going to go vomit in the garbage. We've got 3 of us. Get real. Sam? You're going to have a binomial and a trinomial. What are your signs going across? What's the binomial? What's our trinomial going to be? Evan? Remember, it goes left squared, left right, right squared. So when you do this, what's your left value squared? No, sorry, this part up here, when you take, after you take the cube roots. So this would be this number here squared, then multiply them together, 2x, and then end with a right squared, which would be good. Now, what did you get? You got this that's going to reduce out, which means the function behaves like this parabola, but it's going to have a hole in it. Where's the hole going to occur? Where? What? When x equals 2. You won't see this when you go to your graph. It looks something like this. Plug a 2 in here. Well, here's what we'll say. By the way, what kind of discontinuity, let's identify the type of discontinuity that we have. Sierra, what type of discontinuity do we have? A hole in the graph. Is that removable? Yeah. We just need to plug it with something. I can build a piecewise function that will solve this problem. Here's the first piece of the piecewise function. It's going to be equal to the original everywhere but what value? 2. We need to find something that I can plug in it to in order to make this a smooth curve. You can tell me the number value that the function would need to take on in order to plug that hole. You got 1, 2, 3 of you. What would the function value have to be in order to fill that hole? Look at what the reduced expression is. How did you get the 12?
I didn't go in and out, actually, 16 and previous one.
Yeah. Just evaluate out the reduced expression at 2. So when I do that, I get out a 12. And the function has to take on that value. Now, does this meet the conditions of our continuity trinity? Does the left-hand limit now equal the right-hand limit? Yes or no? It did before. The problem was that function value. Does the function value equal the left-hand limit and the right-hand limit now? In this, absolutely it does. Make sure when you give the graph, you give that whole limit. Questions on that? Next one up. Go through right now, and you are going to sketch a graph of what this piecewise function looks like. You're going to give a Cartesian plane, an XY coordinate plane. Just do an input, comma, output. Notice that there's a transition that's going to happen in there. You shouldn't be dependent on a calculator to do out a piecewise graph. Half of it's going to be a parabola, half of it's going to be a constant function. There's what your graph should look like. Now, don't forget the arrows at the end. John, what kind of discontinuity, is this continuous? What kind of discontinuity do we have? Can we close that off? Is there a way to fix it? Can we fill in a hole? Mm-mm. Keep in mind, what piece of the Holy Trinity of continuity does this not satisfy? Yeah. The left and the right limit don't equal each other. As I approach 1 from the positive side, what value would I get? Cameron, what do you say? What's the limit value as I approach from the positive side? We approach 1 from the positive side. You should have it on your paper. What's it always going to be for x being greater than 1? What's the limit as you approach from the left-hand side? What's the limit as you approach 1 from the left-hand side? Steve? Are these equal to each other? We can't fix that. Okay? Now, what we're going to have you all do now is this. Make sure your names are at the top of your homeworks. Staple together. If you've got multiple sheets, there's a stapler on my desk. I caution you, be very careful. It is it's actually so strong that it is illegal to have in America. This is an illegal. They imported it from China. It was smuggled in. It's very, very strong. Never mind. I don't give away my sources. Careful, cover your eyes. No, it's electric. See what I mean? I mean, wow. Evan, be careful. You're going to get hit with some shrapnel. Watch. Wow. See? Sure, I'll throw it away for you. No octopus tentacles on the side. What we need you to do, hand those up and over now, please, to John. All right, now, whoa. The last thing that we're going to have you do is this. In terms of our checklist for today, let's ask a couple of questions. Did we get done the quiz? Yes. Did we get done our continuity day 1? The next thing that we have to do is let's bounce over to our homework. Your homework is twofold. You have worksheet B due next class, and you have the evens on the limit worksheet that you did, or whichever ones you didn't do the other day. So, what we're going to have you do now is this. Thank you very much. I need you to take a minute, and maybe we should take a picture so you can recall, because the last time that we got you into groups, you left the rows a disaster. There are 4 lines. Notice how they are spaced. Look right in front of you right now. You see what's right there? The front people, make sure you're facing the letter of your name. I'm going to have a heart attack or a stroke up here one day. I just asked 2 things. you be nice to the next teacher that you have for the rest of the year, because they deserve better than you give me. Number two, if I fall in an awkward position, just pose me so I look normal when the EMTs. Get with your groups. You have 10, 15 minutes to complete. Now, I'm going to say this. If your group gets the individual questions done, you can come and hand them in. Your worksheet, whichever one it was that you had, you did have for the other day. I already gave you worksheet B the other day, is that right? Okay, thank you. Thank you.